Hello everyone, I'm Xuan Wang from Nanjing Normal University. It's my greatest pleasure to deliver such simple speech over my mainly focus on rare earth promotion for oxygen electrocatalysis. So first, I can begin my self-introduction for my education and research here, attached here. I graduate from Nanjing Normal University, majoring in computational theoretical chemistry and heterogeneous catalysis. So currently, I'm the postdoctor in the same university here, and during my doctor degree process, I also behaved as the visiting scientist for EMR from Tokyo University in Japan. So as you can see here, my research interests mainly focuses on heterogeneous catalysis, and I also see that some speakers here in this schedule also share the same similar interests. So we can, I think, if we have chance to chat with each other here. So I also attach some corresponding methods from myself. So here from the computation chemistry, I mainly uses ab initio molecular dynamics and electrochemistry simulation to understand the complex change, instant change from from these structures and solid liquid phases to interpret its instant change under the Bell's potentials. But in practical, as for a whole the transformation of the reactant to product, it may experience some other same for complex complement elementary steps. So to fully construct a whole picture of the process, and we still depends on the it depend on the data from the two methods to enter into the machine learning potential training, which I deemed will be the direction for the future performance of molecular dynamics. Why we need catalyst science? Here, I just say that from our researchers, we have noticed that we even with the development of contemporary society, we have transformed from the fuel cells to clean energy to seek the sustain future development here. So the whole driving force transformation of our point of view lies in structural change of energy system, and from the fuel cell to the clean energy such as the windy cloud and sunny and sea powers from the powers from the sea. So within this transformation, we need the catalysis sciences. It will possesses the power to transform the uh, pollutant into the products through the whole loop, and from synthesis, characterization, electrochemical test, and theory prediction standing here. And this is also the direct picture from Professor Noskov here. So in just this one sentence, we need to depend on catalyst science in future clean energy to realize a sustainable future. My research from heterogeneous catalysis largely lies in oxygen reduction reaction and the following evolution process, which will be discussed later. So here I just from the beginning here I just lay some brief discussions for the reduction of oxygen. And as you will see that it may seem to behave as a very simple reaction from oxygen to water and the Bell's potential, but actually it's very complex, I think. So you will experience many elementary steps there, and you will see that it provides mainly the transformation of oxygen intermediates, and it provides the oxidative condition, and throughout these processes we will see that the four electron pathway versus two neutron pathway, they realize the competition between for the current densities. And we here use the theoretical microkinetic volcano plots, which are constructed by Professor Yinsky and Noskov and Karen Chen. So here we need to still use the platinum and the the goal to understand and interpret the whole process. You will see the whole process is limited by the oxygen coverage and the formation of peroxide from under different Bell's potentials. So our group, as you will see that the currently commonly used metals are platinum and gold, or sometimes the silver, but these metals are very expensive. So if we want to replace these metals, we need to seek some such other metals such as the iron and the cobalt and nickel, but these metals are poorly formed. So our group mainly focuses on the rare earth promotion for the electrocatalysis, especially for these non-precious metals, including three aspects here. Why we use the rare earth species? Because the beauty of using rare earth species is that even in small quantities, they can significantly alter material properties, which largely depends on its valence states of the 4F, 5D, and 6S. This special type kind of valence configuration, and we strictly speaking, the rare earth is encompass 17 elements, but typically we focuses on the less right here. It's because of its available 4F electrons. So to understand the rare earth promotion effect, my first work is on the purpose of gradient orbital coupling. The constructed of FPD orbital coupling was proposed first to understand the rare earth promotion for transition metal-based catalysis over the oxygen reduction reactions. At first glance, you will see that it's a little, sometimes you will see it's perhaps a little bit complex, but actually we need to depict here the F orbital can be activated along with optimization of the uranium and oxygen covalency degree. So with this F orbital coupling modulation effect, the more properties of cobalt as is here and here, it will be re-optimized to achieve the good performance for the catalysis samples. So in experiments, we just refers to the hydrogen bond competing crosslink network to attract the positive charged ions such as the uranium and the cobalt to states into the nitrogen doped carbon nanosheets. And after the calcination, we obtain the catalyst sample is here. It's composed of the atomic cobalt loaded onto the uranium oxide and forming the unique structure. So we deem this structure mainly act at the active phase to construct the whole, to proceed through the whole reaction progress. And still in the typical electrochemical test, we measure the three samples in the electrochemistry, and in zinc layer we will perform good performances in oxygen reduction and the zinc batteries here. The second case is still based on the gradient orbital coupling, and you will see that here I provide the catalyst of terbium oxide, and still the atomic cobalt loaded onto the terbium oxide is achieved to form the unit site of terbium oxygen cobalt state. And this here we need to pronounce the gradient coupling orbital coupling construction accounts for the cobalt 3D band narrowing behavior to drive the whole catalysis progress. And still, from the electrochemical tests, we can see that the most performances of these status we presented here from, and also these status have confirmed that the obtained catalyst can behave as the enhancement compared with its counterparts, notably from this CV, the cyclic voltage curves and the polarization curves. So it's a lower hydrogen production indicates it's preferable for electron pathway. And based on the gradient orbital coupling, here we use the more complex model named the Newton-Sanderson-Grimley analysis for the band narrowing property. And what's the trick of the Newton-Sanderson-Grimley analysis? It lies in the narrowing 3D band compared with the fat 3D band to provide the additional overlap and or for the participation of the pi bond in terms of the interaction between active site and the adsorbates. And here you will see that is the beyond the typical sigma bond, it produces the additional pi bond to realize the whole structure, the modulation effect here. So the buffworks are from the oxygen reduction, and here I also provide this discussion for oxygen evolution reaction, which is still another reaction that's quite different from the previous oxygen reduction here. And you will see that the 3 typical pathways are available for the whole reaction. And also, typically, we deem this reaction is energy consuming and they incurs the higher orbital potential. And the direct oxygen coupling should be favored compared with this intermediate. And why AEM is more energy consuming is the universal scaling between the two intermediates limits whole efficiency. So the rare earths can also activate the lattice oxygen for promotion of oxygen evolution here, and use the rare earth elements to activate the whole lattice oxygen to participate into the formation of oxygen to avoid the formation of OH intermediates. So both from experiment and theoretical investigation, we constructed the atomic serum induced the nickel cobalt oxide for enhanced oxygen evolution, mainly from the oxygen mass of 18 to confirm its formation of the lattice oxygen participation here, and it actually reveals the better performance. So if you are very interested in gradient orbital coupling, I will also provide the review article here. The name is Real Evoked Gradient Orbital Coupling for Electrocatalysis, and it will provide more complete discussions for the whole framework. So, as a serious chemistry, I also have developed the multimath code to facilitate the transformation and treatment of some calculation results here. So the multimath currently uses the Python language to construct the whole process, and it will possess some main modules to support for some other kind of types of calculations here. Currently, it's experiencing based on the early versions. I have reconstructed the whole structure to make it more powerful than before. And I will brief discuss how it's available here. So the first module is the symmetry analysis, most for it target at the molecules and the crystal structures. So it mainly serves for the thermodynamic module, the module, and we begin with the symmetry analysis. We can obtain more important properties of the whole systems. Such as the point group for molecules, we obtain the rotational symmetry number. And from the space group analysis, we can achieve reciprocal space, and finally we can get the band structure. Another module is the chemical calculation module. Now, the multimath supports the 4 methods such as listed here for more convenient calculations of thermodynamic quantities. And after catching your provided frequencies, it will remind that users must check your calculation results to avoid some obviously errors. And some more chemical calculation module finally outputs the information like this, so you can use these quantities for future calculations of such as the free energy diagrams. Now, the new version of this module now supports VASP and CP2K. So perhaps in the next, I can support more calculators beyond the two calculators here. And from the beginning of 2020 and 22, I was invited by Dr. Li Su to join the development of CP2K code. And I think this CP2K is getting more and more powerful than any other code to perform ab initio, molecular dynamics, and first principle calculations. So I can support more codes here to combine the multimet and the CP2K into other calculators to facilitate our theoretical chemist post-works. From my point of view, the future prospect for the whole development of electrocatalysis beyond based on the various promotion lies in three areas. The first is the data-driven science and theoretical investigation to use structure and data from the literatures and use them combined with the AI-driven and machine learning and theoretical calculations to provide the basic data and guidance for design structures of the catalysts. Then the second is the synthesis from experiments to the practical application, and the first initial electron measurement of this catalyst obtained here. And with the obtainment of this catalyst samples, and we can further provide the advanced physical calculations to understand its intrinsic properties and its relation between structure and performances. And this whole, I named it as the closed loop experiment framework to expedite the future design and the catalyst samples. So here, this is all my support. Thank you. And thank you for, and also the thing that welcome to our school at Nanjing Normal University. And thank you again.